Hello and welcome back. In this video, we're going to look at this paper which talks about freeform deformations. Once again, displacement fields corresponding to every pixel in the image, and it's a non-rigid registration algorithm, of course, and its application to breast MR images. Okay, so why do we need this in this context of this application? Basically, these breast MR images, these are 3D images of the breast taken for diagnosing and identifying breast cancer, right? So the way they do it is for contrast enhanced MR. So basically you inject the contrast agents, and wherever there is a contrast agent, there is increase in the intensity, right? But it turns out that the rate at which this contrast agent is taken up in the diseased area, that is a tumor, will be different. So it'd be nice to plot this as a function of time. That is, you inject the contrast agent and you sequentially image the same location in the breast and look at where the contrast agent is accumulating. Now, in order to do that, there are some issues, right? Any motion of the patient between the scans, or even a normal respiratory, like it says in the paper, if you just even talk about there's pre and post contrast images. That is, you acquire some images which you do before you inject the contrast. This can be some separate imaging session. I would like to think they are the same imaging session. Of course, there is patient movement between scans, and there is also normal respiratory and cardiac motion. Okay, so which means that if you are this causes some problems because you can't align the images as the contrast accumulates in the tissue and you're still imaging. Okay. So this algorithm basically arises in that context, right? So how do we register successive images, 3D images of the breast taken over time, and it has to be non-rigid registration because most organs are deformable, right? Especially so here we are trying to do this paper from this group talks about how we can use a certain form of regularization, that is smoothing using B-splines, in order to reliably estimate freeform deformations. Okay, so let's go into the paper. So it comes in two steps. One is that it models the registration as a combination of two registrations. One is the global and a local registration. Okay, see, this global registration is nothing but your rigid body registration, just rotations and translations. Okay, so this is a combined transformation they are estimating one, but they are estimated independently. So what is the transformation? That is basically the global transformation. Is your familiar? It's an affine transform model. So this is an affine transform model right there. So that's what they are estimating. So this affine transform model is what they estimate, but this is estimated independently of the according to at least this paper. You can just do this first. Okay, but in order to get to a very accurate registration, you also need local deformations. The local deformations is where you try to do the non-rigid registration. Okay, so here, like in the Demons algorithm, the local deformations are estimated pixel wise with a small difference. Instead of looking at the displacement field of estimating the displacement field of every pixel, which is typically done in Demons, here they do it for a set of control points. Okay, these control points are then basically used by the B-splines. These are B-spline control points, and then they are used to interpolate the deformations to the rest of the pixel. Okay, so the basic idea is if you deform the object, as it states here, by manipulating an underlying mesh of control points. So the control points are where the deformations are estimated, and then B-spline curves are used to interpolate it everywhere. Okay, so we did something similar for Demons. We did do a Gaussian smoothing. Okay, so they don't do that. Instead, this regularization or the constraint is obtained using the B-splines. Okay, So here is how what the model looks like. I will show the models. The local deformation is given by the following formula here. It's basically using cubic B-splines. Okay, how does it work? So we have a set of control points, a mesh of control points nx, ny, and z. And if this actually represents phi ijk represents the deformation at those control points. Control points are uniformly spaced, and of course you have this grid of control points. You can control the size of this grid, either make them coarse or finer. If you do very coarse grids, you get global deformations, and if you are making very fine, then you have very local deformations, right? And in order to regularize this, and we are using B-splines because then it produces a very smooth and differentiable transformation. Okay, so how does this work? So if you look at if you have determined the deformations at the control points phi ijk, then at any point xyz, this formula tells you it's the corresponding deformation. Okay, so how does this work? So all it does is, if you have, let me just explain this first, and then we can show it in the picture. So if all it does is it takes a point x, right, and it calculates the nearest control point. So basically what's happening here, if you see this is calculating the nearest control indices of the nearest control point. This is in 3D, so you have x, y, z coordinates, so you calculate the indices of the nearest control points. Okay, and you also look at the distance of this x, y, z from the nearest control points, both in x, y, and z directions. Okay, this summation here tells you the number of neighbors that's taken into account. So L equal to 0 to 3, M equal to 0 to 3, N equal to 0 to 3. So we are looking at a large number of neighbors for a particular point x, y, z. This many neighbors, right? So because if you see, you are summing over phi of I plus L, j plus m, and k plus n. Okay, so this summation tells you the number of neighbors. Okay, so you can have any number depending on how accurate you want it, or how smooth you want it. Have this, but for the cubic B-spline, this is the typical number used. So this will translate to about 4 into 4 into 4, about 64 control points are used to estimate the deformation at one point. Okay. So you can have this control. So you can have the control point, like I said, very coarse or very fine, but they can be significantly lesser than the number of voxels in your pixels in your image. So that's the advantage. That's one advantage. Second is that since you're using this cubic B-splines, you get a very smooth deformation field because you're using the B-splines for the interpolation, and it's also differentiable. So what do these functions B0, B1, B2, B3? They tell you the weighting of each of these control points based on the distance u. Right? In this case, it's u along x may be v along y, and z along w along z. Distance from the control point. Right? That's what this. If you look at this line of the paper, it tells you how they calculate the distances. Okay. So for every point, you locate the nearest set of control points. In this case, there are about 64 in 3D, and you calculate the distance of these control points from from the point of interest, right? And you use that to calculate use that to calculate the weighting for each of these control points, and then subsequently estimate the value of the deformation field at that point. Okay, so this is the algorithm in a nutshell. So generally, it's of course you can see that it's complicated to code, and we'll also see what kind of loss function is being used. But the first step is you evaluate a global transformation, which is your affine transformation. Once you have done that, then you estimate the local transformation using B-splines. Okay, B-splines interpolation. So you have a mesh of points where you estimate the deformations, and from using that mesh, you interpolate everywhere else using the B-splines. Okay, so those control point estimates will be used to weight the value of the deformation at different locations. Okay, and of course you can you need the B-spline, cubic B-splines to actually do the weighting. So that's the overall idea for as far as using the cubic B-splines are concerned. Okay. So on top of this, there is actually a smoothness penalty which is imposed on the transformation. Correct. So for the basically for the 3D penalty for the spline-based transformation, in order to be smooth, you have the similar smoothness constraints, which is written here in integral form. Basically, the second derivative, square of the second derivative, right? For for the transformation. Okay. So this is just to make sure that you have smooth transformation. Okay. And of course, this is only applied to the non-rigid transformation, and for the affine transformation, the regularization term is 0. So this is the regularization term, the one we see here. Basically, the smoothness constraint using the second derivative of the transformation is basically the smoothness constraint, right? And it's only applied for the non-rigid agitation part. Okay. The loss function on the smoothness constraint, the loss function is your mutual information. Okay. So if you remember the demons, we were mostly there. It will work for images that are from the same modality. But once again, the problem here that we are trying to handle is that we have injected contrast, so the intensity will change. So it's best to use something like this. In this case, the mutual information. So this is the mutual information criteria is the loss function. So the optimization procedure consists of in this case 2 terms, is to minimize the loss function, and so that's why it's negative, and the smoothness constant and the smoothness. Okay, these are the 2 terms. So the smoothness smoothness term should be minimized, and the loss function negative of the mutual information has to be minimized, right? So this is the total loss function. Okay, because this lambda is another hyperparameter, okay, which trades off between alignment and smoothness. Okay, so the algorithm proceeds as follows, as given here. The affine transformation parameters are obtained by maximizing the mutual information, right? So we saw that. Once you estimated the affine parameters, of course you have to apply that, right? Then you initialize the control points. Fine. So initialize the control points, meaning you estimate some rough estimate. We can also be identity transform, but you can also assign some reasonable estimates of the deformation field, and you do this like this particular procedure that's outlined here following this clause. This is for multiple resolution. Okay, so then you calculate the gradient vector of the loss function. The loss function they are talking about here is equation 8. Please look up the paper. That equation 8 is nothing but your smoothness term imposed on the freeform deformation plus the mutual information. Okay, so then once you have that, once you calculate that loss function, you calculate the gradient of the loss function with respect to the non-rigid transformation parameters, which are nothing but the deformations that you estimate at the control points of the mesh. Okay, so there is a threshold on the norm of the gradient of C. As long as it's greater than this threshold, that is, it doesn't go below a certain value, you do gradient descent. Basically, this is gradient descent. Okay, you do this gradient descent, and then of course after you estimate this, you apply the deformation, and then you recalculate the gradient vector, so on and so forth. Okay, and of course once you have converged with for a particular resolution, you can move to a higher resolution of grid points and also the higher resolution of the image, and then repeat the whole process. Okay, so this is the typical procedure for the non-rigid registration using the B-splines. The authors have got excellent results for this. We will look at this demonstration of this in a later class next week. Right, for now, that's just the summary of the algorithm is what we have been trying to give you. Okay, so for this process is like I said, iterative process equivalent to gradient descent, but They used it for this registration process for aligning breast tissue before, pre and post contrast enhancement, right? The environment before and after injection of contrast. So in order to identify, breast lesions much more accurately. Okay. So far in this week we have looked at two algorithms: the Demons registration algorithm as well as the algorithm for estimating these freeform deformation using B-splines regularization. These two are typical algorithms used in this field, very highly cited algorithms, seem to be very effective, been shown to be effective in many applications, but the field is still wide open, a lot of progress being made. People are also using deep learning to assess these kind of deformations. Okay. So we'll see that when we get to the part where we use deep learning for image analysis. That is all for this week. Thank you.